Hey everyone, welcome back, and today let's solve Leetcode problem 36 titled Valid Sudoku. So we have to determine if a 9 by 9 Sudoku board is valid, and note that the size of this input board is going to be fixed. So only the filled cells need to be validated according to the following rules. Each row must contain the digits 1 through 9 without repetition, and each column must contain the digits 1 through 9 also without repetition. And each of the 9 3 by 3 sub-boxes of the grid must contain the digits 1 through 9, again without repetition. So basically we have to have unique digits, or use all the digits from the range of 1 to 9 in every column, every row, and every 3 by 3 sub-box. And note, a Sudoku board partially filled could be valid, but doesn't necessarily have to be solvable. We just have to check if it has any repeating characters, and we don't care if it's solvable or not. So only the filled cells need to be validated according to the mentioned rules. So in example 1, they actually give a nice photo or image of how this actually looks, and we have this nasty input board here that no one really wants to read. But essentially we'd output true. And the reason why is that, as you guys can see, each row and each column each has unique or distinct values from the range 1 to 9, and each sub-box, that's a 3 by 3 sub-box, also has unique values that are in the range of 1 to 9. None of the values in that range are repeated, or none of the values in the box exceed that range. And in example 2, we have the board to be, again, this large input board, and we'd output false because same as example 1, except the board is same example 1, but except with the 5 in the top left corner, it is modified to 8. And we know that in the first column we have an 8 here and an 8 at this index as well, or at this cell. And since we have a repeating character in the range of 1 to 9 in one cell, or one column, sorry, we know that this is not valid because, again, there are two 8s in the top left 3 by 3 sub-box, as you guys can see here, and there's also two 8s in literally the same column, and so it's going to be an invalid input. So with that out of the way, I will give you guys a few seconds to kind of just go over this problem in your head and think of a valid solution, and then I'll show you guys how I would optimally solve this problem. Okay, so honestly, at first, this problem may seem pretty difficult and interesting, but it really has a very nice and really concise problem statement, especially that we're given that our size is fixed. That makes it even easier, right? So essentially, the way we're going to solve this is we're going to use a very simple algorithm with hash sets to track numbers in different rows, columns, and squares, and basically identify if we've found any reused values in each row, column, and 3 by 3 square. So first we actually need to identify, okay, what data structures are we going to use? First, we're going to use three dictionaries of sets, storing all the different elements in each row, column, and square, which is going to help us track which numbers have actually been placed already in each row, column, and 3 by 3 sub-square or sub-box in our input board. And the key point is that each set is going to store numbers that have already appeared, and we're going to check if any number is already in its corresponding set. And if it is, the board is invalid because, of course, we've reused that value in its corresponding set, or row, column, or square. Okay, so with that out of the way, let's just go ahead and dive straight into the code. Okay, so first I'm just going to initialize a default dictionary for columns. And in Python, it's incredibly easy. We just have to say default dict, and we'll pass in a set. I think that's spelled right. Okay, so basically, again, why we use a default dict, each key is basically going to correspond to a column index, and the value is a set that will store the numbers we've seen in that column. And again, this default dictionary with a set ensures that if we access a key that doesn't exist yet, a new empty set is created automatically. That's why default dictionaries are so useful, especially in problems like this. And similarly, we're going to have the same approach for our rows as well. That's also going to be another default dictionary with a set. And if you guys haven't picked up yet, we're going to have also, again, of course, a squares to be another default dictionary. I really hope I'm spelling default dict right. I'm not 100% sure. I think it should be correct. And again, the squares is going to basically have a key as a tuple in this case. Again, the square is a little bit different. And basically, the key is a tuple r divided by 3 and column divided by 3, which represents those 3 by 3 subgrids in the Sudoku board, as each subgrid is uniquely identified by dividing the row and column indices by 3, because that's going to tell us which index or which cell value square or board that we're in of our input board as we traverse through the input, which is also very key. That's the most important part of the solution, actually dividing the row and column cell values or indices by 3 to accurately access which cell or which sub-square we're actually in. Now let's just simply loop through the range of 1 to 9 for the rows and columns in the input board, and it's pretty simple to do that. We'll just say, I'll just say for row in the range of course, 9, because we have a range of 9 different cells for each row, column, and square. And again, we're basically iterating, in this case, through the rows of the board, where row is going to represent the row index. And since a Sudoku board has 9 rows, we'll just use range of 9. And of course, in Python, the for loops are going to basically iterate from 0 to 8, but it still covers, of course, 9 values because it is 0 index based. And we're going to have a nested loop to say for C in the range of course, again, 9. For the same reason, we have 9 columns in each column, square, and subsquare. And again, C is going to represent the column index, and again, there's 9 columns, so that's why we do that. Now we actually have to check if board add index R, add index C in any iteration of this nested loop, if that's equal to the string, I'll just say this, of a dot, then we know it's an empty cell, and we can just continue to the next iteration, right? And as you can see, if we were to scroll back to the problems, all the empty cells are simply denoted as periods or dots, however you'd like to call or interpret them. And that basically means that their cell in the input board is empty, and so we don't actually have to care about that. And we can just, whenever we see an empty cell, continue or move on to the next iteration. We only have to check cells that actually contain numbers. So we just have to skip over this iteration using the continue keyword in Python. Now, this is where we have a little bit of the main chunk of code, right? Honestly, it's pretty simple to understand. It's just pretty hard to code up, so feel free to actually just fast forward, as I'm going to take my time to actually code this out and make sure that I don't spell anything incorrectly or don't have some weird, silly syntax errors here. Okay, so if, I'll just have a nested parentheses, if board add index R index C in this current iteration, where R and C are values in the range of 0 to 8 or 0 to 9 exclusive, if board at index R index C is already in the rows at that R value or cell column, or, in fact, I'll just go down, or board at index R index C is already in the columns at that column cell value or index, or finally, what we were talking about before, dividing the row and column index by 3, or board at index R index C is already in, that value is already registered in our square set of, in this case, we interpret the key to be a tuple, like we talked about before, to be the row value divided by 3 and the cell value divided by 3. If any of these conditionals actually output to be true, then we know we can immediately return false. Okay, and the reason why is, again, we're basically checking if the current number located at board RC is already present in either, if it's already present in row at R, basically the set tracking numbers for the row R, or it's in the columns at C, the set tracking numbers for column C, or it's at squares with the key being a tuple, R divided by 3, C divided by 3 integer division, the set tracking numbers for the 3 by 3 subgrid that contains that cell. If any number or any value at that index RC is already found in any of the sets, as denoted by the OR keyword, it means that the board is invalid, and so we can automatically return false in this iteration. Okay? And ultimately, if that's not the case, then outside of this conditional, we can add columns at index C, our column value, and add, I believe it is, for sets in Python, basically board at R at C, basically the value corresponding to that cell value for that specific column. And we have the similar approach at row at R, dot add board at R at C. And again, like we talked about before, for squares or sub 3 by 3 sub boxes, it's a little bit different. Our key is actually a tuple, so we'll say squares at, in this case, instead of just having values, we're going to actually have a tuple, or integer divided by 3, and C integer divided by 3, oops, dot add to our board at index R index C. Basically adding board index R index C to the current sub box or sub square where we can find out which subsquare that is, dividing our current indices by 3. And of course, that has to be integer division because we want integer indices for our input board. And again, what this does is if the current number is not found in any of the sets, we can add it to the columns at that cell value, tracking the numbers in that current column, the rows at that R column, and the squares tracking the numbers in the 3 by 3 subgrid, as denoted by R and C, integer divided by 3. And this ensures that in future iterations, we can detect duplicates in the row, column, or square. And ultimately, outside of this for loop, if we don't return false for any iteration in this for loop for any board at index R, index C, we can return true, because that would mean that we've basically gone through all the cells in the board without finding any duplicates and without returning false, and so we can return true, again indicating that the board is valid. We don't actually have any duplicates in any of the boards, or sorry, any of the subsquares, rows, or columns. So again, unless I made any syntax errors here, this should be accepted and this should be submitted. Okay, I think this should actually be indented, is what it's throwing at me. But this should be accepted now. And, okay, let's see what's wrong here. Name R is not defined. Okay, yeah, let me just change this to R, just to better simplify this. But now, as you guys can see, this will actually be accepted, and it's just about as efficient as you can get. So to better explain what this code does overall, I'll try my best to talk as slowly as possible and tell you guys, or demonstrate how this would work. So the function works by iterating through each cell in the Sudoku board and using sets to track the numbers that have appeared in each row, column, and subgrid. And as we move through the board, we'll check for duplicates in the corresponding row, column, and subgrid. And if any duplicate is found or any value is repeated in that current set, then the board is indeed invalid and we have to return false. And if we finish checking all the cells without finding any duplicates in their corresponding sets or rows, column, and subsquares, then we know that the board is valid, and so outside of the for loop, we can return true. So for the time complexity of this program, it's going to be, of course, big O of 1 or constant time, because we know that the board size is fixed at 9 by 9, and we're always going to loop through the 81 cells, and all operations inside the loops are always constant time operations like set lookups and set insertions. That's why hash sets and hash maps are so great. And that's why the overall complexity does not depend on the input size, and it's going to be fixed. It does not grow with the input size because the input size is, of course, fixed. And the space complexity is also going to be big O of 1 because the size of the dictionaries, rows, columns, and squares, is again fixed, and each dictionary contains at most 9 keys, and each set stores at most 9 numbers, resulting in a constant amount of space. Again, it doesn't grow as the input size grows. Okay? And just a quick note, the reason why we do R and C divided by 3, assume we were right here. This is going to be index 0, 1, 2, 3, 4, 5, 6, 7, right? What subsquare is this actually in, right? Which row and column is this subsquare in, this 3 by 3 subsquare? If we divide R and C by 3, we know that we're at current R to be 7, and so 7 integer divided by 3 is going to basically be 2. We're in the index 2 subsquare. This is the 0th subsquare, this is the first subsquare, and this is the second subsquare. In this case, C is 0, and so this is going to be in the top of our subsquares in the first column, because C is of course 0, and 0 divided by 3 is indeed 0. We can do this or apply every operation like this for every single 3 by 3 subsquare in this input board, right? So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I'll see you guys in the next video. Bye-bye.